Okay, let's see if we can work through this. Apologize if there's any interruptions while I'm going through this, but I'm trying to minimize those, but I'm not sure if I'll be able to. First one, absolute value greater than 9. That's going to make us, if you remember, we have to do that portion, and then we write OR, and we do 12 minus 4x, but now we flip the inequality and then do the opposite of 9. Remember, we had a rule ax plus b is greater than c, then that provided ax plus b is greater than c, or ax plus b is less than negative c. So that's all I've done here. I'll go ahead and solve this. Negative 4x is greater than negative 3. Divide by negative 4, so we get x to be less than 3/4. Here we go, do the same thing. We get negative 4x is less than negative 21. Divide both sides by negative 4. I get x to be greater than 21/4. Graphically speaking, now I know it doesn't ask for a graph, but I like to put one in here. What we're saying there is that we're getting those values there, those values there. So putting that in interval notation then would be negative infinity to 3/4 union 21/4 to infinity. And there's the reason why I like to write the graph. The next one, this is a rational inequality. So if you remember, we need all the, basically created sign chart here. So we need all the zeros. So there's a 0 at negative 4, there's a 0 at negative 2, and there's a 0 at 3. And those come from setting each one of these factors equal to 0 and solving. Then you write all your factors on the left-hand side, x plus 2, x minus 3, and I'm going to write x plus 4 squared because that shows up twice. And then my total. Okay, there is a 1/3 factor here if you want to put it in, but 1/3, no matter where I choose these intervals, 1/3 will always be positive, so it's not going to impact the end result. So now I just go through and I start evaluating these things. So choosing test values to the left of negative 4, to the right of negative 4, and evaluating each of these. So then if I do that, this is going to be negative, negative, and then positive. This will be negative, negative, and then positive as well. This one here will be positive, negative, positive. And the last one's going to be positive, positive, positive. And that's just taking, like I said, take the number 5 and plug it in here. 5 plus 2 is a positive number. 5 minus 3 is a positive number. 5 plus 4 squared is a positive number. And then doing that for each one of these. Here, and inside here, I used 0. So 0 plus 2 is positive. 0 minus 3 is negative. 0 plus 4 squared is positive. Now if I look at my totals, these are all being multiplied and divided together. So I'm looking for basically odd negatives, and that would make a total that's negative. But here I've got even negatives. So my total here would be positive. This total would be positive. This total would be negative. This total would be positive. This is saying we want less than or equal to 0. So that's negative numbers. So we're looking from negative 2 to 3. Those are the only ones providing a negative. And that's what we've got. So negative 2 to 3 is that interval notation. The last one on the first page. It's a root equation. Root equations, you're going to have to square things, but we have to isolate the root before we can do that. So I get that. Now I'll square both sides. So squaring both sides makes the right side 2x plus 3. Makes the left-hand side 4x squared minus 20x plus 25. Solve this for 0 then. I get eventually 4x squared minus 22x minus 22. Sorry, plus 22. Plus 22 is equal to 0. I'll factor a 2 out. Gives me 2x squared minus 11x plus 11 equals 0. I can divide both sides by 2 because it is an equation. So essentially it just goes away. So now I'm solving that thing. And when I solve that thing, I'm looking for quadratic formula basically because that thing's not going to factor real nice. So x is equal to 11 plus or minus root 121 minus 4 times 2 times 11 all over 2a. And that becomes 11 plus or minus, that discriminant is 33 over 4. Now, remember when we square things, we probably introduce extraneous solutions. So these things approximate to 4.19. and 1.31. I just want to double check which one works. Now, just because I rounded those things, there's going to be some rounding concerns here that we got to pay attention to, but it shouldn't be too bad. If I go 2 times 4.19, so I'm doing the left-hand side of this equation, I get that number there. Now I'm going to do the right-hand side, so I go 5 plus root of 2 times 4.19 plus then 3. Hit enter. And those two numbers are extremely close to one another. So I'm gonna make the argument that 4.19 is a correct answer, and that ends up being 11 plus root 33 over 4 as an exact value. If I try the other one, 1.31, basically I'm just going to recall that, and instead of typing 4.19, I'll type 1.31, get that number there, and then do the same thing here. 4.19 needs to go to 1.31, and I get that number. And obviously those are different, so there's my extraneous solution. 4.19 is the only answer. All right, so go to the second page. Second page, height of the projectile is modeled by that, where t is in seconds and ht is in feet. What is the maximum height attained by the projectile? If you think about maximum heights, it's finding the maximum of any quadratic equation. X is equal to the opposite of b over 2a. Okay. So in this case, this is not, and they do this on purpose, it's not in the right format. Negative 16 t squared plus 84t plus 180. That's going to give you the b and the appropriate a. So opposite of b would be negative 84. And then actually I should be using t here. And then over 2a, so negative 32. So we'll take negative 84 divided by negative 32. So 84 divided by 32 gives me 2.625. 2.625. Okay, that is the time, right? That is the time. They want the maximum height. Okay, so that's the t coordinate, and we're going to find the maximum of this thing. Okay, that's the t-axis. We just found the time in which it occurs. H of t is going to be that point right there. So we need to take this 2.625 and plug it in there to evaluate. So I'm going to go negative 16 times 2.625, that quantity squared, plus 84 times 2.625, plus then 180. And we get 290, this height right there is 290.25. So that's what they're looking for in point A, is the 290.25. When does the projectile reach its maximum height? Okay, that was what we found right there. So that's a 2.625. Okay, it says when will the projectile hit the ground? Well, that is when this thing's equal to 0. So I'm going to go negative 16t squared plus 84t plus 180 equals 0. Now, most likely, this will not be really factorable real easy. So let's jump straight to the quadratic formula. Opposite b plus or minus b squared minus 4ac all over 2a. And that should then give me my times. Okay, now those are 2 times. So we got to find out which one is positive. So I'm going to pull this at negative 84. Do it this way. Negative 84 plus square root of 84 squared minus 4 times negative 16 times 180. Okay, so that should be the numerator. And we'll divide that by negative 32. Okay, so that's a negative time. So that's the, really what's happening with this picture is that it's actually doing something like that. And that t that we just found is that one. Well, time can't be negative, so that's not the solution we're looking for. Basically recall that, And now we're going to use this negative sign there, which would be changing that to a minus. Hit enter, and 6.88 ends up giving me the time that this thing comes back to the ground. These are all things that you could go to Y1, type that in, and you go find maximums and intercepts and all that kind of stuff, get the same exact answers. So if you want to use your calculator, go ahead and do that. 6 says the graph of the function is provided, find h of 0. Okay, h of 0, that is the height at 0, so x being 0. Okay, so the y value that I get back is 1. Remember, this is an input, and those are x values. That's an output, and that's your y value. Find the domain and range of h. Domain, remember, x values. Okay, so I take a vertical bar and start passing this thing through here, and the x values that vertical bar intercepts are going to be my domains. So first x value I come across is -2. Now there's an open dot there, so I don't include -2. And I keep going through, and the last x value I come across would be 3. Now there's a closed dot at 3, so I do include that. So that's the domain. The range is the same concept, but now we just use a horizontal line. You start at the bottom, and you start traversing that thing through. So the first y value I come across is -2, and I include that because it is an ordered pair, and that ordered pair includes -2. I go through, and the last y value I come across would be 3. So -2 to +3, and in this case I'll include 3 as well. So that's my range. It says find the values of x for which h of x equals 3. So they're asking what values of x, what input values will give you a y value of 3 back. Well, there's a y value of 3 right there. Okay, so we're looking for the x value that provides us with, and that x value is -1. Find the values of x for which h of x, your y's, are less than or equal to 3. Well, which x values will provide me y values that are less than or equal to 3? Okay, find the values of x that provide y values that are less than or equal to 3. Okay, well, if I look at this, aren't those all my x values are doing that? Every x value I plug in here is going to give me a y value that's smaller than or equal to 3. So in this case, it's all my domain. It's -2 to 3, including 3. Now, if it said like 2, it said this number here was 2, then you'd be saying, okay, what x values provide me y's that are less than or equal to 2? So that starts off maybe an x value of -0.5 all the way to an x value of 3. Okay, so that's all we're doing there. Find the intervals for which this function is increasing. Okay, increasing means it's going up. Y values are getting bigger. So from -2 to -1, those are the x values in which this y's are getting bigger. And then over here, this one I got to kind of guesstimate. I'm going to say it's like a 1.2. X value of 1.2 to x values of 3. We're going up as well. This function is increasing, and we union those. Now, if it's asking me where it's decreasing, decreasing would be from there to there. So from x value of -1 to an x value of 1.2 maybe again, that thing is decreasing. So if you know where it's increasing, you also know where it is decreasing. All right, we'll do this one, sketch the graph of the function. It's a piecewise function. When you do piecewise functions, you just need a series of points for that. Graph those, create maybe a table. So I'm going to just say, here's my x's, and here are the p of x's that would go with that. If x is 0, I'm always going to use that point, whether it's included or not. If I plug in 0, so the square root of 0 is 0, take the opposite of that, it gives me 0. Now I'm going to go square root, I'm going to choose x to be 4. Square root of 4 is 2, but now it's opposite, so -2. And then I'll do, I could do 9, gives me 3, it'd be -3. But I think that's probably enough. 1 might be a good one to use as well. Square root of 1 is 1, opposite of that would be -1. So I've got enough points here, 0, 0, 4, -2, and then I'll go 1, -1. So that's enough to give me that curve. Okay, now I'm going to do this one. Let's do that one just in blue. Okay, so here's my x values, and here are my p of x values. So if x is, I think a good point, this is an exponential, so we should know when x is 0, we get 1 back. Well, actually, let's do it this way. Kind of silly to do it that way. Erase this. With piecewise, and we did it in the red one, but wasn't paying attention in this blue one. We want to start with that number there, and then usually the numbers that are in that list. So start with x to be -1, so I get, plug that in, I get 3 to -1, which is 1/3. And then I want numbers that are to the left of that, so I'll go, x to be -2, so I get 3 to -2, which becomes 1/9. I go -3, so I get 1/27. So what we're seeing here is when I use -1, now -1, I'm going to go to 1/3. So I put an open dot at 1/3. And then at -2, it's 1/9, and at -3, it's 1/27. And we know with exponentials that the horizontal asymptote is the x-axis. So this thing kind of looks like that. That's a piecewise function. Obviously, these are, it's because I just chose a random function, but these are really hard to graph, but still doable. We had to approximate them. The next question says, state the domains. Remember the domain of combining functions. The domain of any combined function is the intersection of f's domain with g's domain. Okay, so maybe I write it domain of f intersect the domain of g. So the domain of f, remember, we just have to take square roots of positive numbers or 0. So I take 2x minus 4 is greater than or equal to 0. I get 2x is greater than or equal to 4. So x has got to be greater than or equal to 2. So that's the domain of f. X greater than or equal to 2. And then I do the same thing for g. X plus 3 is greater than or equal to 0. So then x has got to be greater than or equal to -3. So domain of g, x is greater than or equal to -3. Now if I want the domain of f minus g, it's just the intersection of these two things. So if I plot these, x being greater than or equal to 2 would be that stuff. X being greater than or equal to -3 would be that stuff. Where they overlap is your intersection. So they start overlapping at 2. So the domain goes from 2 to infinity. Okay? Or just say x is, because let's say x is greater than or equal to 2 would be fine as well. Then what f minus g? Well, that's pretty easy. We just take root 2x minus 4 minus then root x plus 3. Then once you evaluate the expression f composite g of 2, remember that means f of g of 2. So all you're going to do is find g of 2. Okay, so I find g of 2, plug 2 in there, and I get square root of 5. So now I'm going to find f of the square root of 5. Okay, so now I take square root of 5 and I plug it in right there. So I get root 2 square root of 5 minus 4. And that's, you can put that as a decimal, you can leave it that way, that's fine. I think on the final this is probably going to be, say, maybe like 6. So then when I find g of 6, that would actually turn into 9, and take the root of that, I get 3. So now I have an integer that I'm plugging in this one. Might be a little bit easier on the final. Last one's asking you to find the inverse. Okay, so if you remember, we just basically write this as y, 5, 2x minus 7, and now we just try to solve for x. So I'll multiply both sides by my denominator. So we get y, 2x minus 7 is equal to 5. Try to isolate x now, so I'll divide both sides by 5. So we get 2x minus 7 is equal, or sorry, divide both sides by y. So we get 5 over y. Solve for x then, so I get 2x equals 5 over y plus 7. And then I will divide by 2, which is the same thing as multiplying by a half. So it's going to give me 5 over 2y plus 7 halves. That is the work to solve for x, but now with a finding the inverse, once you do that, once you isolate x, if you remember the last technique, last step is to take the x's and make them y's. and make the y's x's. So that would be the inverse. All right, this one's just a kind of a recognition of your facts for polynomials. It says there's a local maximum at x equals 4 right there, and that is a local maximum. Okay, it's larger than any value, y value that's close to it, so that's true. The 0 of x minus 1 has even multiplicity, so that one there, even multiplicity would be something like this, tangency. Here we pass through that 0, so this would be false. Tangency is even multiplicity, passing through is odd multiplicity. It says has an odd degree. That is a factor, and that is a factor. Those are my zeros. This one is odd degree, so let's just say that is just a first degree multiplicity, one multiplicity of that 0. Let's say this one is 2, okay? That means that I have one factor there and I have two factors there. That would be odd. Okay, let's see if, well, what if this would have been a third degree? Okay, well, if that's a third degree and that's a 2, that's 5, still odd. If that was 5, that's still 2, still odd, right? All right, so let's say that this one was changing. Let's say that was 1, this is 2, that's still odd, but what if this was a fourth multiplicity? 1 plus 4 factors is still odd, right? No matter how I do this, as long as I maintain this one to be odd and this one to be even, an even number plus an odd number gives me an odd number. So this is an odd degree polynomial. That's true. P of x has a positive leading coefficient. Well, if it's odd, remember odd, I didn't want to delete all those. That was true. That was false. That was true. Any odd polynomial, odd degree, is going to look like a cubic. Okay, and that, so that's like a times x to the third. Okay, so the end behavior, as x goes to the right, my y value is going right, or positive. As x is moving to the left, my y value should be going negative for a positive a value. Right here, in this example, as I move to the right, it's x is going, or y values are going down. Here, as I move to the left, my y values are going up. So this blue curve needs to be flipped. So when I flip it with a negative, it's going to look something like that. So it has to have a negative leading coefficient. Here it says P of x divided by x minus 4 must have a remainder of 0. This is kind of targeting the synthetic division, the remainder theorem. And remember, if your remainder is 0, that's telling you if P of x is 0, meaning that you have an x-intercept. And so at basically this 0, which is 4, we're going to see if we have visually in the graph the crossing at an x-intercept. And we do. So that would be a true statement. Okay. It says P of x is a one-to-one function. That means it passes the horizontal line test. And we can see, maybe if I use that horizontal line, it fails the horizontal line test. So this would be false. True, false, true, false, true, false. Number 11. This is a difference of perfect cubes. I will give you this formula. But a cubed minus b cubed is always going to be of the form a minus b, a squared plus ab, and then plus b squared. Where in this case, a is just 1x, and here b is the cube root of that, okay? Because this is, basically I could rewrite this as x cubed minus 5 cubed. So your b would be 5. So then we're going to go, so this is x minus 5, and then it becomes x squared plus then a times b, which is just 5x, and then plus 25. Now if I multiply that all out, I should get back to that. They want the zeros, okay, as exact form. So this one, you have a 0 of 5 from that. But this thing here, you're going to have to use a quadratic formula. So x is going to equal, I'm not going to go through all the simplification, but b squared would be 25 minus 4 times 25 times 1 all over 2. So those are my zeros. You can leave it that way if you want to as your final answer. Number 12, asks you to find all x, y intercepts, vertical and horizontal asymptotes, any holes. So first thing you gotta do is factor this thing. So we got top is x plus 3, x minus 3, bottom is 3, x plus 3, x minus 2. Remember, first thing you want to do is look for common factors. That's a common factor. So it gives me a hole. So I have a hole at x equals negative 3. If I want to find the location of the hole, obviously the x is equal to negative 3. If I want to find the y value, I plug negative 3 back into the reduced version. So here's the reduced version. If I plug that negative 3 back in, I get negative 6 up top. And on the bottom, I would get plugging negative 3 and negative 5 times 3 would be negative 15. So I have a hole at negative 3, comma 6/15. If you just tell me x equals negative 3, I'll probably give you full credit for that. Asymptotes. Okay, remember vertical asymptotes are from the denominator equaling 0. So x minus 2 being equal to 0, so I have a vertical asymptote at 2. X-intercepts are when your numerator is equal to 0. So in this case, I get x equaling 3. And then horizontal asymptotes, when the top, the leading term in the top is x squared, the leading term on the bottom is also x squared. If I were to FOIL that all out on the bottom, it's x squared. But up top, the leading coefficient would be 1. On the bottom, leading coefficient would be 3. If you remember, when these terms are the same, you simply just look at the leading coefficients, and that gives you your horizontal asymptote at 1/3, and it's y equals 1/3. On the final, I don't know if, you might have to do a hole. There might be a hole, there might not be a hole, there might be, leading terms. This one might be, this denominator might be, or power might be the same. It might be bigger, which would be a different rule. It might be smaller, which is a different rule. So make sure you investigate that series of information and understand it fully for all the different case scenarios you could come up with. Here it says how long will it take an investment to double if the interest rate is 7.5% per year, compounded continuously. So that is compound continuously. Remember, the amount after time t is equal to your principal times e raised to the RT. So we want something to double. I don't care how much I have. I just want it to double. Okay. So they don't tell me my principal, so I'm just going to let it be 1. If I want that to double, then it become 2. So I'm inserting $1, and I want to find out how long it will take to become $2. E, my interest rate, 0.075, and now t. Okay, t is what I'm looking for. It's how long will it take. I'm looking for time. So we get that. So really I've got the equation 2 equals e to the 0.075 t. Well, that's a logarithm, or sorry, exponential equation. We use natural log to get that variable out of that exponent. So I take the natural log of the right-hand side, and it gives me 0.075 t ln of e. If you remember ln of e, that's just 1. So now I've got essentially that equation. So then we'll take and divide both sides by 0.075. So natural log of 2 divided by 0.075 gives me t, which would be 9.24 years. 14 is a half-life question. What I want you guys to understand and know, and I might write this on the board, but your rate for a half-life is always ln of 1/2 divided by your half-life. Okay? But the population, the growth model here is the same. It's we usually write a of t is equal to a sub 0 e. A lot of times they say r or k t. If you think about that, that is exactly the same as just using different variables of a of t equals p e to the rt. It's the same thing as compound continuously. But with the half-life, with decay, your r value is going to become negative, and that happens because of this ln of 1/2. So I'll find the rate first. So R, or I'm going to go ahead and put R in here. Make a little bit more explicit what we're talking about. So that's the rate of decay. So they're saying we start with an initial amount of 6 billion. Okay. E, now R to the T. R I don't know yet, but T is 7 hours. Okay. Half-life is the time that we put right here. So R is ln of 1/2 divided by my half-life of 4. And I'm just going to write that as ln of 0.5 divided by 4, and then times T, of 7. That was my time. And I'm going to type that thing into my calculator directly like that. And this is exactly what you can do on the final. 6 billion, so 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. Then second E, ln of 0.5 divided by 4. Okay, I'm going to do it this way so nothing gets messed up. Put another parenthesis, then times by 7 to keep that product of 7 in my exponent. I think that will be enough, and I get that. Okay, so what's that? Comma there, comma there, comma there. So approximately 1.78 billion. Okay. All right, so this next example, or next question is getting into vertex form. In vertex form, if you remember, is simply completing a square. So you're going to set this thing, you're going to go negative x squared minus 10x. You put your 24 over here. I'm going to do this. I'm going to make this negative 24. I'm going to make this positive x squared and positive 10x. Makes things a little bit easier if that's a positive. Half this and square it, so it gives me 25. Add 25 over here. So now this thing here becomes a perfect trinomial. So we got x plus 5 squared is equal to, then this side over here is 1. So now I'm going to get this back to equal 0. So 0 is equal to x plus 5 squared minus 1. And then I want to make that 0 just g of x. And now I've put this thing in vertex form. So the vertex is at, remember now with a parabola, that's negative 5. You move that, adding to the x moves it left and right. Sorry, adding moves it left, subtracting moves it right. So we added, so we move it left. And then this is going to move it down, so minus 1. So there's my vertex. Graphing this thing real quick. The vertex is at negative 5, negative 1, negative 5. Negative 1 would be there. Okay, so what I guess what I did, I kind of overlooked this. I went through and I multiplied everything by a negative here just to get it into being able to complete the square a little bit easier. But if I go back and look at this, to get back to this, I do need that negative there. So if we go ahead and start evaluating this thing, that way you'll get your formula there, or your equation there. So this, I do need that negative, because that's going to tell me then my domain. Now remember, this negative here tells me it's concave down. So concave down looks like that. So now my domain, this is a parabola, so your domain is polynomial, so your domain is all reals. But my range in this case is just from negative infinity up to this y value, which is negative 1. And having that picture of that graph will help me find that range a little bit easier. This one's not too bad. We'll do this. Logarithm sums. Remember that turns into a product, so log base 4 of x plus 1 times x plus 2 is equal to 1. Well, that goes to x squared plus 1x, 2x, 3x plus 2. So we got log base 4 of that is equal to 1. Now I use the definition of logarithms, so 4 raised to the first will come back and give me this argument, x squared plus 3x plus 2. Solve this for 0. So we get 0 is equal to x squared plus 3x minus 2. So then I get, what's that? I guess nothing really multiplies together. You give me negative 2 and adds up to be positive 3. So use the quadratic formula there. I'm going to leave that up to you to find that. When you do the quadratic formula, make sure that you plug back in here and make sure your answers give you positive numbers inside those logarithms. You only take logarithms of positive numbers. All right, I will continue to work on this. I'll finish these up this evening, but I think that first 16 questions might give you a good start on that review.